All right, our very last section is 9-8, collisions in 2 dimensions. So if you can do it in 1, why not try 2? Might as well. And the big idea here is what I've underlined in the learning objectives, that we should apply the conservation of momentum along each axis. So along the x-axis and the y-axis, and they are independent of each other, just as we saw with projectile motion. So let's take a look. Okay, so here we have a elastic collision. It says it's a glancing collision that conserves both momentum and kinetic energy, so it must be elastic, right? We have a projectile that comes in to hit a stationary target, and now they bounce off at an angle relative to each other. What we're going to do is apply the conservation of momentum along each axis, x and y, and then apply the conservation of energy for elastic collisions. Remembering energy does not care about directions. So even though it's not always conserved, it is useful in the fact that it does not need to worry about direction. So looking at an example here, we want to find the equations for this figure that has a stationary target in terms of just the masses, the initial velocities, the final velocities, and those two angles that it ricochets off at. So I encourage you to pause and take a stab at writing these equations out yourself. And if you don't know, that's okay, but see what you can do to get it done. So ready, set, pause. All right, let's take a peek. So if it's an elastic collision with a stationary target, then along both the x and the y direction, we expect the momentum will be conserved. Even if it was an inelastic collision, these top two equations would still apply. So we have our initial momentum and our final momentum. Our initial momentum in the x direction is just the mass times the initial velocity. It's moving purely in the x direction. The target is stationary, so it does not have any momentum. The final case, though, notice we have momentum in both ball 1 and ball 2, but it's not all of it because we care about the direction. We only want the x component of this final momentum. So that means we want the x component of these final velocities of v1f and v2f. And so with these, you're going to have to break it down into those x and y components, right? So this is going back to our vector where we have a v1f. And so we want to break it down. I'll get a different color perhaps. So we could have an x component, which would be our v1f x. And then we could also have our y component of this vector. Sorry that my arrows don't perfectly line up. Those tips should be together. But that would be our v1f sub y. And it also mentions this angle theta 1. Now, because theta is defined relative to the x-axis, then that tells us that we can use our classic cosine for the x component, right? Cosine of theta 1 will be v1fx divided by v1f. So v1fx, the x component of the momentum, could be written as v1f times cosine of theta 1. Back to my blue color. So all of that is the v1 f x. And similarly for 2, right, it would be following v2f cosine of theta. So it's still taking the cosine to get the x component of it. In the y direction, it's a little bit more interesting. The initial momentum in the y direction is 0 for both of them because neither of the balls is moving in the y direction initially. So we just put in a 0 there. Cool, no velocity in the y direction. Now, in the y direction, to get the y component, we are going to have to use sine. right? That's the opposite over the hypotenuse. Cool. So that's pretty standard and familiar. One thing we'll have to take into account, though, is that V1Fy is in the negative y direction, right? So that's why we have this extra negative sign out in front, because it is going down, and you need to specify that it's going in the negative y direction. If you had written this as a positive, then you'd have plus one answer plus the other, two positives somehow coming out to 0. There's no way for them to do that. So that negative is in fact pretty important. So let's put an arrow pointing to that. Negative. So it's a bit of work to get there on breaking down the velocities into x and y components. But once you do, it's very stepwise in writing it out, and it will follow this basic procedure. So pretty familiar equations. Energy is in many ways the easiest because you just care about the speed at which they are moving. So the target's not moving, V2I is 0 initially, plus 1/2 m1 v1I squared. Cool, it has some speed, and we'll square that. And similarly on the final cases, you again just have the total velocity or speed without any mind of direction. So you can take that V1F, the total magnitude of the velocity, square it times m1 1/2. Same thing with mass 2 and V2F squared. So these are the equations for a stationary target, and there are 7 unknowns. Since we know that our V2I is equal to 0, we don't have a full 8, we just have 7. That means if we know any 4 of these variables, whether, let's say, m1, m2, v1I, v1f, then we can solve for the remaining ones. We could solve for the 2 angles and the final velocity of 2, for instance, because we have 3 equations, so we can solve for up to 3 unknowns. So they're a pretty powerful set of equations. This is again applied in elastic collisions, which is why we have the conservation of energy. But even if it was an inelastic collision, the first 2 equations would still apply because they're just conservation of momentum, which is pretty powerful. Okay. And finally, I'll mention this clip of a movie analysis of physics in the excellent Spider-Man movie. So I encourage you to check it out. The person who made the video did an analysis using some of the concepts we learned this particular chapter. So take a look, I'll post a link to it. And that pulls us through chapter 9, where we saw center of mass and the idea of linear momentum. Please feel free to ask questions in the discussion or send me an email or stop by my office hours. I'd love to chat. Take care, y'all.